some work going. Okay, so what we're going to be looking at here are reaction mechanisms, and we want to be able to do this stuff a little bit Hess's law style. So they're going to be proposed reaction mechanisms. So they're going to give maybe 2 or maybe 3 or maybe 4 reactions as possible steps to get to an overall reaction. Okay, so we want to be able to look at these different reactions. These elementary step, they call them elementary step reactions. So these, different smaller reactions that we're going to add together to give us our larger reaction. And a lot of times what they're going to do is they'll be like, all right, well, this is the slow step in the process. So that's the rate determining step. And we'll be able to get a rate law by looking at that particular reaction and anything that happened before it. Okay. So a couple vocab words here that we want to take a look at. So when they talk about elementary steps, they're just looking at the small reactions that add up to give you the total. So for example, down here on the bottom, these are all elementary reactions down here. Our elementary steps are those 3 reactions there. Those would be like elementary steps. That's what they're talking about when they talk about an elementary reaction. Okay, and a lot of times what they do with those is they'll label them like fast or slow to let you know which one's fast, which one's slow, and we'll look at that as we kind of move forward here. But sometimes they'll ask for the molecularity, very rarely, but they do this. So that's why we're covering here real quick. They want to know like the molecularity of that particular reaction. So of the elementary step reaction. So all you really need to do is look at the reactants. If there's one reactant, it's unimolecular. Okay. There's 2 reactants. It could be AB or AA. They're bimolecular then. Bi for 2. Okay. And this could be also written as like 2A. They wrote it like that. That would also be considered bimolecular too. And one that is kind of rare is the termolecular one, and that's where you have 3 reactants and products all coming together and colliding at once. Okay, so yeah. Okay, so if we look down below here, they're asking us, okay, what's the molecularity of each of the 3 steps that you have? Okay, of each of these elementary reactions. Well, if we look at each one of those, how many reactants do we have for each? There are 2. Yeah, there are 2. So we got these 2, right, for both of those reactions. Then this one here, we have 2 NOs. So there are 2 reactants for each one of those reactions. So all of these guys here will be considered to be bimolecular. Okay, would be considered to be bimolecular. All right, and the second part of this here is they're asking us whether or not the sum of the elementary steps is the net reaction, which is this one up here above. This is the net reaction, right? That's the overall one, our kind of the end product of our Hess's law, right? We're adding these reactions together, and hopefully it gives us this. Well, if we go ahead and look at these, remember, we can cross out intermediates, right? Which are basically things that are produced by one reaction and consumed by one of the other ones. So, for example, here we've got N2O2 and N2O2, right? It's a product of that elementary step, but it's used up in that one. So we can cross those out, just like we would in Hess's law when we're adding the reactions together. Anything on the reactant side and product side, we can cross them out if they're the same. All right. So another one there would be N2O, right, here and here. And then we can just add all the elementary steps up together, and we get 2NO plus 2 hydrogen going to a nitrogen and 2 H2O. And there we go. We just showed that, hey, this does match our net reaction. So we're all set. That's all you gotta do. Yeah. Okay. All right. Go to the next one here. So reaction mechanisms and rate expression. So this is where we're going to use these reaction mechanisms and combine it with our rate law stuff, okay, to give us like a simple rate law expression. So a few things that I want to highlight in here this to make sure that we make mention of. So like I said, they're gonna give you different elementary reactions up in there, and they're gonna label them fast and slow, just like how they're doing down here in the problem. Like they'll label the different reactions slow and fast and stuff, and they'll let you know what's going on there. Okay, those are determined, so they talk about that stuff being experimentally determined. All right, and basically you just need to make sure you can take note of the slowest step, because that is going to be a rate determining step. So that's really important. We want to be able to identify the slow step and use that as our rate determining step, because that's what's going to help us write rate law. Okay, so that'll help us write the rate law. Okay, and just our reaction intermediate, right? That's something that's produced in one elementary step of the reaction and used up in another. Okay, so if it's on the product side and the reactant side in those elementary steps, we want to get rid of it. Okay, and remember, a catalyst is a substance that comes out of the reaction unchanged, right? So it's not listed in the final reaction. Just keep that in mind. You guys remember what a catalyst does? How? There we go. Okay. Lowers the EA, right? The energy of activation, or the activation energy, right? And that, as a result, speeds up the reaction. Okay. All right, so in order to figure out whether or not our reaction mechanism, okay, so our proposed elementary reactions here are any good, all right, we have to go through a couple different things. All right, so first thing we got to do, cross out any intermediate catalysts, okay? So those are the ones that are on either side of the reaction. We're going to cross all those out. All right, we need to add together, like we did in the first problem, and determine whether it matches the given reaction for us. Okay, so when we add these two reactions together, they better match that one. If they don't, it's no good. Okay. All right, and then a couple other things here that we want to make note of is 3 and 4 are important because we want to be able to draw a line through the rate determining step that's going to help us out. And term rate law not include any steps after the slow step. And then we can determine whether or not it matches the rate law of the reaction. So and I'll give you some examples of what that means in terms of, we'll hit one here when we start looking at our reaction mechanism. Okay, so as we look at this reaction, okay, we've got our balanced equation right here. They're saying, okay, the experimentally determined rate law is that. Okay, all right, that's fine. So, and then the suggested mechanism for the reaction is below. All right, so they give us this two-step reaction mechanism. All right, so we have to determine whether or not it's acceptable. All right, so in order to figure out whether or not it's acceptable, we've got to do, so first thing we got to do is after we add reactions together, we gotta figure out, does it match the net? All right, remember this is, so this, we've got to add these guys together. All right, we're going to add these two reactions together. We got to get it to match this. If it doesn't match, it's no good. We can throw it out right there. Okay, so we're going to cross out the intermediates, which are fluorine here. So we get 2NO2 plus F2 goes to 2NO2F. All right, it matches. All right, check that. We check that box. Okay, darn it. means we got to do some more work. Okay. Very often, I mean, I think I've come across maybe a problem, maybe two problems where it hasn't matched. Okay, the first time. All right, it's very rare that it doesn't match. So usually what you have to do is you've got to go to the slow step and anything before. And figure out if rate law matches. Okay, so what we want to look at here now is I'm gonna highlight just the slow step. Here it is. Right? If there were other steps before it, I would highlight those as well, just to get a rate law from those steps. Okay, we're going to ignore the second step because it says it's fast. So I'm just going to look at the rate determining step, and we're going to use the just the stoichiometric ratios in there to figure out if, hey, does it possibly match? So the way we're going to do this is we're just going to write our rate law for this reaction is equal to rate times K times NO to the first and F2 to the first as well. Okay, and I'm just taking that from the the mole ratios, okay, in the reaction there. All right, and this matches too. Right? Okay, that matches. All right, so check. So if that works, our rate law matches just looking at our slow step. Okay, we can say, all right, well, the reaction mechanism, it is acceptable. Yes. All right, yes, it is acceptable, right? We add the reactions together. They give us the net reaction. We get a rate law based on the slow step. We're all set. Okay. All right, so let's do another example that is slightly different than this, but it's kind of similar. Let's do 1996 first, and then we'll do 1990. Yeah. All right, so do 96 first. So we want to write a balanced equation for their overall reaction here. So we just need to add all those guys together. Okay, crossing out all of our intermediates. So we got 2NO. I'm just going to write it over here because I can't fit it there. Plus 2H2 going to plus 2H2O. Okay, so what are the intermediates here? Well, we've got N2O2 and N2O. And why are they our intermediates? Yep. Right. They're in products and reactants of elementary steps and are used up. Okay, they're used up during the reaction. Okay. All right, so the next part here is from the reaction, from the mechanism represented above, a student correctly deduces, okay, they're saying it's correct, that the rate law is this here, rate is equal to K times this guy. All right, right, that is, what order is that? It's third order, yep. Okay, so they're saying the reaction's third order. Okay, the student then concludes that, number one, the reaction is third order. Okay, great. And number two, the mechanism involves a simultaneous collision of two NO molecules and an H2 molecule. Are conclusions 1 and 2 correct? Explain. Okay, so number one, I want to show you where that third rate law is coming from, like where they're drawing that rate law from just from looking at the equations. Okay, what I'm going to do is I'm going to highlight the slow step and any reaction above it, because those are the steps that are going to be involved in our rate law, that we're going to write our rate law from. Okay? Oh boy. Oh my gosh. There we go. All right, I'm back. There we go. Okay, so we're going to write our rate law based off of these two reactions here. So rate is going to be equal to K. And notice how many NOs we have. We've got two of them, right? On our reactant side, we got two of those. We're not going to include any intermediates in our rate law. And how many hydrogens do we have in there on our reactant side? Just one. Okay, do you see that? So, yes. Because the slow step is our rate determining step. So the reaction will proceed normal until that step. That's going to slow it down. Okay, so we only care about the reactions to, including to, the slow step and anything prior to it. Okay? All right? So that's where that rate law is coming from. So the student, and they told us it was correct, right? But that's where that's coming from. I just want to make sure that we can, that's how it's a little different from the one before, because the slow step was the first step. So there's nothing ahead of it. All right? So ignore anything after the slow step when you're looking to write the rate law based on these elementary steps. Okay, now this next thing they tell us is, hey, they're saying the reaction mechanism involves simultaneous collision of 2NO and H2 molecules. Simultaneous, what does that mean? Same time. This is written, these reaction mechanisms. This happening at the same time. Are 2NO molecules and an H2 molecule coming together at the same time? No. Okay. First, it's telling you no. See, right? So it's telling you no, combine together first, and then you get the reaction with the H2. Okay. So no. All right. Simultaneous collision doesn't happen. It happens in two steps. Okay. So one is correct. The assumption that it's third order. Okay. Number two, not correct. Okay. Reaction mechanism has reactions. Well, I should say it has three reactions, but NO and NO are in one step, and the H2 are in another. Right? So it doesn't happen simultaneously, it happens in separate steps. They react in separate steps. Okay. Okay. All right, so the last one here is just a kind of reaction rate sort of question. right? Explain why an increase in temperature increases the rate constant. So what does an increase in temperature cause? Right, rate it increases K. Okay, why? Why is that happening? All right, well, here we go. Look, we gotta have for a reaction to happen. This is what we need to have. You gotta have collisions, right? You gotta have collisions. Number two, yes.
As the temperature increases, the number of high energy collisions increases.
Yes, that is true. So, because that's what I want to get at, right? We gotta have collisions for a reaction to happen. Number two, the collisions have to happen with enough energy. Okay? Because what do we got to get over? Addition energy, so we got to check that box. And then in addition to that, you also have to collide in the right orientation. And the molecules have to fit together in the right way, so bonds are going to be broken and bonds are going to be formed. It can happen. All right? So it's like, I kind of relate this to almost a clap, right? Okay, if I want to have a nice, solid clap, I bring my hands together with enough energy, right? Because if we collide with this right orientation, not enough energy, nothing happens, right? I mean, we get nothing. You get, okay? Got to have enough energy, right? But if they make it collide with enough energy, but the wrong orientation, right? You get nothing there, no product, right? So you got to have the right. So it's have the right orientation and enough energy to get a good clap, right? Okay, so you got to have all three things happening, right? We got to have collisions. We got to have collisions with enough energy. We got to have collisions with the right orientation, right? So if we increase the temperature, however, said, hey, we increase number of collisions because molecules are just moving faster. We're going to have more collisions, right? And you increase the number of collisions with enough energy to overcome EA, right? Energy of activation for a reaction to happen. Right? So if you increase the temperature, you increase particle speed and movement, right? Which means you're increasing flat out the number of collisions that particles are having, and you're increasing the amount of energy that they're colliding with. Okay? So even if, and for every particle collision, say only 2% end up in a reaction. Well, now if you increase the number of collisions, as the particles are moving faster, even if it's still only 2% of collisions result in a reaction, you get more collisions in less time, right? So you get more product in less time, right? In addition to that, you're moving those reactions, they're colliding with more energy, so the likelihood that you get a reaction increases as well, okay? So you got these particles moving fast enough, all right, to overcome that reaction, or to overcome the energy of activation, okay? So there we go. There's that one. All right, let's do this one real quick. All right, hey, describe two factors that determine whether a collision between molecules of A and B result in a reaction. What did we just talk about? What do we got to have? Orientation. And what? And activation energy. Okay, you got to have proper orientation. We got to have enough activation energy for a reaction to happen. How would a decrease in temperature affect the rate of the reaction shown above?
It would make them less likely to collide and less energy.
Right, it's going to decrease rate. Less collisions, all right, etc. Okay, we want to write the rate law expression that would result in a reaction preceded by the mechanism shown below. All right, so we want to get rid of our intermediate. So we're canceling out A and B. And I'm going to highlight the reaction, the slow step, and anything prior to it. So we got to write our rate law based off of that. So what should the rate law be equal to? Yeah. It sure is. Concentration of A times concentration of B squared. Great. Very good. Everybody see where that's coming from? Okay, we've got our 1A right here. Oop. A, and then our 2B's right there. Okay. Explain why a catalyst increases the rate of reaction but does not change the value of the equilibrium constant. What's a catalyst do for you? Great. Lowers our energy of activation. Okay. It also usually does this by ensuring collisions with the proper orientation. So in grad school, I used to work on silica surfaces, and they're very commonly used for catalysts because you can engineer the silica surface to bond the molecules in a particular way. And when those molecules come together, if you get them right next to each other on the silica surface, they're oriented in a particular way that if they just bump into each other, they're going to collide in the right orientation every single time. So you get reactions that happen very quickly, right? So every collision almost results in a reaction every single time. So if you think about an industrial scale of, these companies that are trying to produce large amounts of a particular product, if they can figure out a way to do it with a catalyst, right, where they don't have to worry about heating up the reaction or cooling it down or keeping it cool or something along those lines, because you think about the amount of energy that it would take to warm up a pot of water, right? Think about thousands of liters that you're going to have to warm up if you're doing large industrial scale type reactions. To do some of this stuff, the amount of energy that you can save by trying to figure out if a catalyst can work the reaction or not is tremendous. Okay, so because energy is, whether heating something up or cooling it down or whatever, you got to spend a lot of energy to do that in the large volumes of an industrial sort of scale. So that's something that they're always constantly looking for shortcuts or things to ensure that reactions happen with a high success rate, like that. So that's about it for today.